Welcome to Lesson 3 of Complex Analysis. In this lesson, we'll cover some basic identities concerning complex numbers. We'll talk about the triangle inequality, distances between complex numbers, and something called a metric space. Some basic identities for complex numbers. As we see here, we have three listed. You have the complex number added to its conjugate, and you take 1/2 of that and you'll get the real part of the complex number. This one's similar for the imaginary part. There's quite a few listed here. I'm just listing the theorem on this page. We'll prove the ones in bold in the following 3 slides, and then the ones that are not in bold I'll leave to the reader to do as exercises. And just to point out here, the theorem 113 is a reference to the book that I've made freely available. I'll be using the numbering from the book, which this is actually chapter 4 in the book, so that's why the number is so high. Okay, we're going to prove the first few of the identities on this slide. We let z equal I plus I y and w equal u plus iv. And before I get started, just a reminder, the conjugate of a real number is the real number itself. The conjugate of an imaginary number is the negative of the imaginary number, and the modulus of a complex number is the square root of x squared plus y squared. Okay, so the first one is 1/2 z plus its conjugate, and we write that out. You see where the imaginary parts cancel, and we get 1/2 2x, and that just equals the real part of the complex number. So second one is the modulus of z by definition equals the square root of x squared plus y squared. And since y squared is a real number squared, it's positive, which means this whole quantity here is bigger than this, and the square root of x squared is the by definition, the absolute value of the real part of z. The conjugate of the conjugate, we just plug in x minus iy and then take the conjugate again. We flip the value twice and we get back to where we started. If you take the modulus of the conjugate and fill in the x minus iy here, then you just square x and square minus y. You get x squared plus y squared, the square root of that, and again, that gives you the modulus of the original complex number. Z, the modulus of z times w, we need to use the rule for the product. It's basically x times u, and then iy times iv, which gives you the minus yv, and then iy times u, this term here, and then x times iv, it's this term. Use the formula for the modulus. You square this, and you square the second, the imaginary part. You write that all out just using basic algebra and keeping in mind that this term here, the middle term here, and the middle term here cancel. And then you can take this term, the xu squared and the yu squared, factor out the u squared, and do the same thing with this term and factor out the v squared. Then you can factor out x squared plus y squared from each of these, and you get x squared plus y squared times u squared plus v squared. And that just gives you the modulus of u, modulus of z times the modulus of w. On this slide, we have the proof of a few more identities. The first one here, the modulus of z over w, we just break it up as z times 1 over w. Then we use the previous identity that the product of two complex, the modulus of the product, I should say, is the modulus of one times the modulus of the other. Then 1 over the w is just the inverse of w. We computed that formula in the second lecture. We get this here, and then u squared plus v squared is a real number. We can pull that out, and we get this expression. Then we take the modulus, the u minus iv, which is the square root of u squared plus v squared, which we can divide into the bottom and the denominator. And then we have this expression here. And of course, what's in the denominator is the modulus, the w. So we've proven this identity. The next one's a bit more involved. It's the conjugate of a quotient. We break up the quotient as z times 1 over w. Then we've previously proven that the conjugate of a product is the product of the individual conjugates. So we get this here. And then again, using the identity for 1 over w, which we used above in this expression. So we get this here, keeping in mind that u squared plus v squared is real. So when you take the conjugate of this, you get just u plus iv. And then this here is in fact the 1 over the conjugate of w. That's probably not readily apparent. So I have another line here to show why this is equal to 1 over the conjugate of w. So 1 over the conjugate of w equals 1 over u minus iv. And here we just multiply by 1, but in an unusual form, u plus iv plus u plus iv. On the numerator, we get u plus iv, and in the denominator, we get u squared plus v squared, which is what we had here. Okay, so take a look at these, because they're going to come by fairly quickly when we get to the more advanced part of the class. And I'll try to refer back, but I can't reprove them every time. So you might want to just go through these a second time to make sure you have the ideas down. On this slide, we prove the final two identities from our theorem. Let's have a look at the first one. We have the conjugate of z times z. We just put in what's the conjugate here, x minus iy times z, multiply it out, and we see that we get the square of the modulus, in which this expression can be rewritten as 1 over z times the conjugate of z over the modulus of z squared. And that only holds true when z is not equal to 0. For the final identity, we have the conjugate of z to the nth power equals z to the nth power, then taking the conjugate. You can either prove this by induction or using the binomial theorem, which I've written up here to remind the listener, and we're going to use that approach actually. So here we have the conjugate of z to the n equals I minus y to the n. We put in x for a in the binomial theorem and minus iy for b. We get this expression. Then we factor out a minus 1 to the n minus k. And we get this. And this turns out equals z to the n, and then taking the conjugate, which is not completely clear, but this further explanation may help a little bit. If we let alpha equal z minus k in this expression here, then we have minus 1 to the alpha, and then we have I to the alpha. Just focusing on those two parts of this expression. When alpha is even, we have minus 1 to the alpha, which of course is going to give us 1 times I to the alpha. I to the alpha is either plus or minus 1. So that gives us a real valued term in this summation. However, when alpha is odd, we have minus 1 to the alpha, I to the alpha, minus 1 to an odd number is minus 1. And then you get minus 1 times I to the alpha, and alpha is odd, so you get either plus or minus I. the minus 1 changes the sign. So for each imaginary term in this summation, you're basically inverting the sign. So effectively, you're taking the conjugate of this, which is what we wanted to get in terms of our final result. If this is still a little bit unclear, what you might want to try is taking n equals, say, 3 and doing it on, taking this thing and raising it to the third power, and then taking the z to the third power, and then taking the conjugate, and you'll see how the terms equal each other. And it's basically what I've explained here, but I admit it's a little bit hard. You need to think about it for a few minutes for it to set in. On this slide, we have the so-called triangle inequality. We see it right here. The modulus of z plus w is less than or equal to the modulus of z plus the modulus of w. The way we're going to do this is work with the square and then take the square root of both sides. So you can see here just plugging in different identities along the way. We have the square of a modulus is basically the complex number times its conjugate, which I've written here. And then we can expand this out here as just the individual sums of the conjugates. Multiply that out, we get all these terms. And then z times z conjugate and w times w conjugate give us this term and this term here. We just bring the z times w conjugate down, and then we rewrite this term as the conjugate of z times w conjugate. And the middle two terms here, when we add them, it's basically a complex number plus its conjugate, and that equals 2 times the real part. We proved that before. Then this real part here could be negative, so it's less than the absolute value, which is why we get a less than or equal to sign. And then we use another identity. The absolute value of the real part of a complex number is less than just the modulus of that complex number. So we have another less than here. And then this is simply, this middle term is 2 times the modulus of z times the modulus of w. And that gives us z plus w squared. Take the square root of both sides and we get the desired result. And we can also substitute minus w for w in here, and then when we put in minus w in this right-hand side, that's the same as the modulus of w, and then we get this variation of the triangle inequality. The modulus of z minus w is less than or equal to the modulus of z plus the modulus of w. In this slide, we're going to look at additional variations on the triangle inequality. The first one is we take the modulus of z, we write it as z plus w minus w, and we group the z and the w together, and then we apply the second form of the triangle inequality to this, and we get that it's less than or equal to z plus w plus the modulus of minus w, which is equal to z plus the modulus of z plus w plus the modulus of w. And so we can just subtract this term here, the modulus of w from the modulus of z, and we get that the modulus of z plus w is greater than the modulus of z minus the modulus of w. And by symmetry, we could have just switched the order of the w and the z, and we also get this expression here. So putting this and this together, we can write it this way. The modulus of z plus w is greater than or equal to basically the absolute value of the modulus of z minus the modulus of w. All right, so that sometimes comes in handy. And if we replace w with minus w in this formula, you see here we get this this result, remembering that the modulus of minus w is equal to the modulus of w. And then just one last thing, which I won't prove, but you can prove this through it by induction. If you can take multiple complex numbers and you have sort of this extended triangle inequality, which I'm showing here at the bottom of the slide. Okay, on this slide we're talking about the difference, or the distance between two complex numbers. So if we have z equals a plus bi and w equals c plus di, we can define the distance the same way we do in Euclidean two-dimensional space, and that's just a minus c squared plus b minus d squared, which is in fact the modulus of z minus w. It seems quite natural, and that's one of several possible metrics that could be defined, but this is the one that's typically used. And I just give a simple example here. If we take z equals 2 plus 3i and w equals minus 1 minus I, and then use this formula to find the distance, we have 2 minus a minus 1, which of course is 3, and then the 3 minus a minus 1, which is 4, and we square each one, so we get 3 squared and 4 squared. We sum those up, we get 25. The square root of that is 5. There's something called a metric space, which is used quite a bit in the analysis of complex functions and even real functions. We're not going to use this a whole lot in what comes afterward, but I thought it would be useful to mention here. So the metric that we defined, the Euclidean metric that we defined in the previous slide, is a metric space. There's three different properties that the distance function needs to satisfy in order to be a metric space. The first one is that the distance is greater than or equal to 0, and it equals 0 if and only if the complex numbers are the same. So that's hopefully pretty obvious from the way we define distance. Also, I think obvious is the symmetry here. The distance from z to w is the same as from w to z. Then a little bit more involved is what's called the triangle inequality for the distance function. And if you have three complex numbers, z sub 1, z sub 2, and z sub 3, the distance from z1 to z2 is less than the distance from z1 to z3 plus the distance from z3 to z2. And we can prove it here. We just write the distance out. It's z1 minus z2, taking the modulus of that. Then we can basically put in a minus z sub 3 plus z sub 3. Then we group together as shown here. Then use the triangle inequality we proven earlier. So this expression is less than the modulus of z1 minus z3 plus the modulus of z3 minus z2. And then by definition, this term is equal to the distance from z1 to z3, and the second term is the distance from z3 to z2.